For more than 2,000 years, one idea sat untouched at the foundation of all matter. The Greek philosopher Democritus, around 400 BC, imagined that if you cut a piece of gold in half, then half again, and kept cutting, you would eventually reach a fragment that could not be divided any further. He called it atomos, meaning uncuttable. It was a guess, an act of pure imagination, but it endured. For centuries, the atom remained the ultimate full stop of physical reality, the smallest brick from which everything was built. By the Victorian era, this ancient guess had hardened into scientific certainty. In 1808, the English chemist John Dalton gave the atom mathematical weight, proposing that each element was made of identical solid spheres with fixed masses. Hydrogen was the lightest. Oxygen was 16 times heavier. Chemists across Europe filled notebooks with atomic weights, arranging elements into tidy tables. In 1869, Dmitri Mendeleev laid them out in his periodic table, and the pattern was so beautiful it seemed to confirm everything. Atoms were real. Atoms were solid. Atoms were the bottom of nature. The word itself carried a promise. Nothing smaller could exist. To suggest otherwise was almost a contradiction in terms, like proposing a piece of the number 1. Physicists pictured these atoms as tiny billiard balls, hard and featureless, bouncing off one another in gases, locking together in crystals. James Clerk Maxwell, the greatest theoretical physicist of the age, described the atom as a manufactured article, unchanging and eternal, stamped from the same die since the beginning of time. There was no crack in it, no interior, no parts. The certainty was total, and it was everywhere. Textbooks taught it. Laboratories assumed it. An entire civilization of scientists built their understanding of chemistry and physics on a foundation they believed could never move. And yet, in a handful of laboratories across Europe, a strange new instrument was beginning to glow. A sealed glass tube, emptied of air, produced an eerie light that no one could fully explain. It looked harmless, almost decorative. But inside that quiet green glow, the 2,000-year-old certainty of the indivisible atom was about to be broken forever. The trouble began with emptiness. In the 1850s, a German glassblower, an inventor named Heinrich Giesler, perfected a mercury pump capable of drawing air out of a sealed glass tube more completely than anyone before him. When his colleague Julius Plucker sealed metal electrodes into these evacuated tubes and passed a high-voltage electric current through them, something extraordinary happened. The glass began to glow. As the pumps improved and the air inside grew thinner, the light shifted and changed. By the 1870s, tubes emptied to a fraction of atmospheric pressure produced an eerie greenish glow on the glass wall opposite the negative electrode, the cathode. Something was streaming across the vacuum, striking the glass and making it fluoresce. Whatever it was appeared to travel in straight lines. The English physicist William Crookes placed a solid metal cross inside one of his tubes and watched it cast a sharp shadow on the glowing glass behind it. Something was being emitted by the cathode and blocked by the metal. Crookes called these mysterious emissions cathode rays. They could be aimed, they cast shadows. They could even turn a tiny paddle wheel placed in their path, suggesting they carried momentum, that they pushed. Crookes became convinced he was witnessing a fourth state of matter, a radiant matter beyond solid, liquid, and gas. But nobody could say for certain what these rays actually were. Across Europe, physicists filled their laboratories with these glowing tubes, each one a small window into an unknown. The rays could be deflected by a magnet held near the tube, bending as if they were being pushed sideways. They heated metal targets until the metal glowed. They passed through thin sheets of gold foil. Every new experiment produced a new clue, and every clue seemed to contradict the last. Were they a form of light? Were they charged particles? Were they vibrations in some invisible medium? The green glow was beautiful and maddening in equal measure. It sat there in laboratory after laboratory, quietly performing its mystery. refusing to explain itself. And around it, a fierce scientific argument was beginning to take shape, one that would divide the physicists of two nations. The argument split Europe almost cleanly in two, along a line that ran between Germany and Britain. In Germany, the dominant view was that cathode rays were a kind of wave. The influential physicist Heinrich Hertz, who had brilliantly proven the existence of radio waves in 1887, ran experiments that seemed to confirm it. When Hertz passed cathode rays between two charged metal plates in 1883, the rays did not bend. Light was not deflected by electricity, and neither, apparently, were these rays. To Hertz and his colleagues, this was powerful evidence. Cathode rays must be disturbances traveling through the ether, the invisible medium that 19th century physicists believed filled all of space and carried light itself. In 1892, Hertz went further. He showed that cathode rays could pass straight through thin sheets of gold foil. How could solid particles pass through solid metal? Waves could ripple through matter, but particles surely would be stopped. His assistant, Philip Lenard, built special tubes with thin metal windows and demonstrated the rays escaping into open air. The German case looked strong. Cathode rays were waves in the ether, weightless and immaterial. But across the channel, British physicists were unconvinced. They pointed to the way a magnet bent the rays, curving them into arcs exactly as you would expect from a stream of moving charges. Waves of light were not steered by magnets. Something with electric charge was clearly moving through those tubes. The British suspected the rays were particles, tiny charged pieces of matter hurled from the cathode at enormous speed. The problem was that Hertz's failed electric deflection experiment stood in their way. If the rays were charged particles, why hadn't electricity pushed them sideways? The two camps talked past each other, each holding half the evidence, neither able to deliver a decisive blow. The rays cast shadows like particles, passed through foil like waves, bent in magnetic fields like charges, and ignored electric fields like light. It was a genuine paradox, and it demanded not another opinion but a decisive experiment, performed with greater care than anyone had yet managed. That experiment would come from Cambridge, from a modest laboratory, and a man determined to settle the question once and for all. The man who would end the argument was not an obvious champion. Joseph John Thomson, known to everyone as J.J., was born near Manchester in 1856, the son of a bookseller. He had intended to become an engineer, but his family could not afford the apprenticeship fee, so he turned instead to mathematics and physics. It was a fortunate detour. By the age of 28 in 1884, Thomson had been appointed to one of the most prestigious posts in science, director of the Cavendish Laboratory at the University of Cambridge. The appointment stunned the scientific community. The Cavendish had been founded in 1874 and led first by the legendary James Clerk Maxwell, then by Lord Rayleigh. Now it was being handed to a young man with almost no reputation as an experimenter. Some senior figures doubted he was ready. Thomson, it was said, was clumsy with his hands, so awkward with delicate apparatus that his assistants preferred he not touch the equipment directly. But what Thomson lacked in manual dexterity, he made up for in insight. He could see through a problem to its essential design, and he could inspire the skilled technicians and students around him to build exactly what he imagined. Chief among them was his assistant Ebenezer Everett, a gifted glassblower and instrument maker who turned Thomson's ideas into working experiments. Under Thomson, the Cavendish became a magnet for brilliant young researchers drawn from across the world. The laboratory itself was modest by later standards. Cramped rooms filled with brass fittings, glass tubes, induction coils, and the smell of hot wax and rubber tubing. But it hummed with ambition. Thomson had become fascinated by cathode rays and by the maddening deadlock between the German and British interpretations. He believed the rays were particles, and he believed the failure of Hertz's electric deflection experiment held the key to proving it. Thomson suspected Hertz had made a mistake. He reasoned that the traces of gas remaining in Hertz's imperfect vacuum had shielded the rays from the electric field. If he could empty his tubes far more completely than the Germans had managed, the rays might finally bend. He set to work. Thomson began with the one effect nobody disputed. He brought a magnet near his cathode ray tube and watched the glowing beam curve smoothly to one side. The direction of the bend told him something crucial. The rays behaved exactly like a stream of negatively charged particles in motion. A positive charge would have curved the other way. Every magnetic test pointed to the same conclusion. Whatever these rays were, they carried negative electric charge, and they had momentum, but the magnet alone could not settle the debate. Because the Germans had their trump card, Hertz's failure to bend the rays with electricity. If the rays truly carried charge, an electric field between two metal plates should push them sideways, just as a magnet did. Hertz had tried exactly this, and seen nothing. Thomson was convinced he knew why. In Hertz's tubes, too much gas had remained. When the rays passed through that residual gas, they ionized it, knocking charges loose. Those loose charges gathered on the metal plates and canceled the electric field before it could act on the beam. The experiment had been sabotaged by imperfect vacuum. So Thomson turned to his glassblower, Ebenezer Everett, and demanded better. Together they built tubes evacuated far more completely than anything Hertz had used, pumping out gas until only the faintest trace remained. Inside, Thomson placed two parallel aluminum plates, and he connected them to a battery so that one plate was positive and the other negative. Then he switched on the beam. At first, with gas still lingering, the ray refused to move, exactly as it had for Hertz. But as the vacuum deepened and the last traces of gas vanished, the beam suddenly responded. It bent, sliding cleanly toward the positive plate, drawn by the electric field. The negative particles were being pulled toward the positive charge, precisely as theory demanded. The German objection collapsed. Cathode rays were not waves in the ether. They were charged particles, deflected by both magnets and electricity, and their charge was unmistakably negative. Thomson had settled a debate that had divided a continent, but a far greater question now opened before him. What were these particles, and how much did each one weigh? To answer that, he would need a measurement of extraordinary cunning. Deflection was not enough. Thomson knew that bending the beam only proved the rays were charged. To weigh the invisible, he needed a number, a ratio that would betray the identity of whatever streaked across his tube. In the spring of 1897, inside the Cavendish Laboratory, he designed an experiment of ruthless elegance. He would set two forces against each other and let them fight to a standstill. First, he switched on the electric field between two brass plates. The beam bent, curving toward the positive plate, tracing a bright arc of green light on the glass. Then he added a magnetic field, arranged so that its push opposed the electric one. Slowly, carefully, he adjusted the strength of each until the beam snapped back to a perfect straight line. At that instant, the electric force and the magnetic force were exactly equal. And when two forces balance, arithmetic takes over. Thomson could now calculate the velocity of the particles, a staggering figure, tens of thousands of kilometers every second, a fraction of the speed of light itself. But velocity was only the doorway. With the magnet switched off, he measured how far the electric field alone deflected the beam. Combining the two readings, he extracted the prize, the ratio of charge to mass. It was a quantity no one had ever pinned down for cathode rays. The apparatus was crude by any modern standard: hand-blown glass, wax seals, a vacuum coaxed out with mercury pumps over hours of patient labor. Yet the measurement was repeatable. He ran it with hydrogen in the tube, then air, then carbon dioxide, then changed the metal of the electrodes. Aluminium, platinum, iron. It made no difference. The number stayed the same. Whatever these particles were, they were universal, identical, indifferent to their source. And the value of that ratio was enormous, around 1,000 times larger than anything measured for a hydrogen ion in electrolysis. Thomson stared at the figure on his page. It could mean only two things. Either the charge was impossibly huge, or the mass was impossibly small. Neither answer belonged in the physics of 1897. And the second answer was about to break the atom open. The ratio pointed one way, and Thomson did not want to follow it. A charge-to-mass value 1,000 times greater than hydrogen's could be explained by a monstrous charge, but every experiment in electricity argued against that. The charge had to be ordinary, which meant the mass was extraordinary. The particle carrying these rays was roughly 1,000 times lighter than a hydrogen atom, the smallest thing in the known universe. Later measurements would sharpen the figure to about 1/836 times lighter, but even the rough number was catastrophic. For over 2,000 years, since Democritus first spoke of the atomos, the atom had been the floor of reality, the thing that could not be cut, the final brick beneath everything. Now Thomson held evidence of a fragment smaller still, a splinter of matter shed from the metal electrodes, identical whether it came from aluminium or platinum. He tested the conclusion from every angle. Perhaps the particles were charged atoms of some light gas, atoms broken loose in the vacuum. But the universality defeated that idea. No gas gave a different result. No electrode gave a different result. The particle was the same everywhere, which meant it belonged to no single element. It belonged to all of them. It had to be a common ingredient, a piece present in every kind of matter. The logic was inescapable and terrifying. If a particle 1,000 times lighter than hydrogen came out of atoms, then atoms had insides. They were not solid, uncuttable spheres. They were structures, assemblies, things with parts. Thomson, a cautious and careful man, understood exactly how much he was risking. To announce this was to contradict Newton, Dalton, and the settled confidence of Victorian science. Colleagues might call it madness. He checked the vacuum, the pumps, the plates, the readings, again and again through the early months of 1897. The number would not move. The particle was real. It was subatomic, and it was hiding inside every substance on Earth. Thomson stood at the edge of a discovery that would rename the smallest scale of existence, and in April, he would step off that edge in front of an audience of his peers. On the evening of the 30th of April 1897, J.J. Thomson rose to speak at the Royal Institution in London. Before an audience expecting a report on cathode rays, he delivered something far more dangerous. The rays, he declared, were not waves in the ether. They were streams of particles, tiny bodies of negative electricity, common to all matter, and smaller than the atom itself. He called them corpuscles. The word electron would come later, borrowed from another physicist, but Thomson always preferred his own careful term. The reaction was not applause. It was silence, then doubt. One distinguished listener told him afterward that he thought Thomson had been pulling their legs. To suggest a particle inside the atom was to violate the deepest assumption of chemistry and physics, that the atom was the indivisible bottom of nature. Many refused to accept it. The Germans, still committed to the ether wave theory, resisted for years. But the evidence did not fade, and Thomson pressed forward, gathering more measurements, refining the charge, confirming the mass. If atoms contained these negative corpuscles, a new question arose immediately. Atoms were electrically neutral, so where was the positive charge? Thomson answered in 1904 with a model that would define a decade of physics. He imagined the atom as a sphere of diffuse positive charge, with the tiny negative corpuscles embedded within it like fruit in a pudding, the famous plum pudding model. It was wrong, as later work would show, but it was the first serious picture of an atom with internal structure, and it framed the problem that Rutherford and Bohr would go on to solve. Slowly, the impossible became the accepted. The corpuscle earned its place, and its new name stuck, the electron. It was the first fundamental particle ever identified, the opening of a door no one could close. Thomson had not merely found a new object. He had proven that the smallest brick of matter was itself a house with rooms inside. And from that single glowing tube in Cambridge, an entire century of physics and the machinery of the modern world was about to pour out. In 1906, J.J. Thomson received the Nobel Prize in Physics for his work on the conduction of electricity and gases for discovering the electron. There is a quiet irony that 7 of his research assistants would go on to win Nobel Prizes of their own, and that his own son, George Paget Thomson, would win one in 1937 for showing that the electron behaves as a wave. The father proved it was a particle, the son proved it was a wave. Both were right, and quantum mechanics would reconcile the paradox. The electron did not stay in the laboratory. It became the beating heart of the 20th century. Every radio valve, every vacuum tube, every early television screen guided streams of electrons exactly as Thomson had bent his beam across the Cavendish. The transistor, invented in 1947, tamed the electron in solid silicon and launched the computer age. Every microchip, every phone, every screen you have ever touched is choreography of electrons, the same particle first weighed in a hand-blown glass tube in 1897. In physics, the electron opened the subatomic frontier. Rutherford found the nucleus in 1911. The proton, the neutron, and eventually a whole zoo of particles followed, mapped by the machinery of modern physics, from Millikan measuring the electron's exact charge in 1909 to the vast accelerators of today. The electron remains, as far as we know, truly fundamental, a point with no parts, no size, no interior. In finding it, Thomson had reached something smaller than the atom and cracked open the deepest assumption in all of science. For over 2,000 years, from Democritus to Dalton, the word atom meant the uncuttable, the final and indivisible floor of the world. On an April evening in Cambridge, that idea ended. The glowing green beam that so many had puzzled over turned out to be a message written in the smallest handwriting in nature. And the message was simple, and it changed everything we know about matter. The atom was never indivisible.